Given what was said now about Maxwell's equations describing all electromagnetism, we see that if we have a magnetic field changing with time, it can create an electric field. A changing electric field with time can create a magnetic field. That also then means that if you have a changing electric field, if you were to produce it in such a way that it also produced a changing magnetic field, it would go back and continue to produce an electric field and go back and forth, back and forth. And in that case, then, you could actually use electric and magnetic fields to create each other with some sort of constant thing until you have some other object get in the way and stop that. And this will work so long as you actually have the electric and magnetic fields basically perpendicular to each other, and they would then be traveling along in a certain way. So if I had a three-dimensional coordinate plane like so, let's call this the x direction, y, and z, or z if you prefer. And if I had the electric field up pointing along in the y direction, and I had this, again, being time variable, if I had this oscillating up and down in the y direction with time, then it should produce a magnetic field. And if it's such produced that it is going to be along in the z direction here, so this will be, so the only way this is going to be maintainable is if this is going to actually be moving along perpendicular to both. So that way we get some sort of, in effect, like a cross product between the E and B fields. Now you might ask, well, what is moving along in the direction of that velocity vector? Well, it doesn't need to be a charged particle, and in fact it'd be kind of hard for that to be the case. If there were a charged particle there, well, for it to somehow, say, produce a changing E field, it would have to, say, be speeding up, or have to be like changing its size of charge, which we don't know how to do that. If it were, say, speeding up and slowing down to change the magnetic field, well, then it's not moving along with a constant velocity. So whatever is there is actually chargeless. Now you might say, then, if it's chargeless, how can it possibly produce an electric field? But of course, remember, it is being produced by the changing magnetic field producing the electric field is changing as well, so it's again inducing the magnetic field and back and forth. So it's self-maintaining. Now it has to get started in the first place. So for example, I have a charged particle, I oscillate in some sort of way so it produces an electric field, but then that electric field is oscillating, produces a magnetic field, etc. So whatever this is that's propagating is something that doesn't actually have electric charge. It also doesn't have magnetic charge, since, as we said, that doesn't exist. So to describe better what's going on, we could take a look at Faraday's law that shows the relationship between the electric field and the changing magnetic field. In particular, of course, we're talking about the changing flux of the magnetic field, but we're not having any surface areas that are changing. So it's the B field itself that has to be the thing that's changing. But notice this equation as it is, that there's a relationship between the changing of the B field with time and this part of the equation. This is basically looking at the electric field in terms of a spatial dimension, say in the x direction. So if we're looking in the x direction here, there's some sort of relationship with how E field is. And here's how the B field is being affected by a variable changing in time. So the book goes through some derivations if you want to look at that, try to see how things go. But basically what it's going to show along the way is if we look at the electric field oscillating up and down as we had drawn before in the y direction, and we look at that oscillation for some length L, that there's a way that we can look at a tiny little bit of how the E field is changing, that the right side of this equation here can be approximated as whatever length we're looking at in the y direction, and how much that E field is changing with the movement in the x direction, And you might be noticing I'm writing my what looks like D symbols a little bit differently. That's because the symbol that I'm using here is basically to say I'm taking this derivative here with respect to the x variable, and the function I'm taking a derivative of, the x function here, the e function I should say here, the electric field function, can be a variable of, or a function of more than one variable. It could also have a y, a z, for example, components. So this is to clarify that I'm taking the derivative here with only respect to x. So this much will then be true for a nice small dx. We can then look in the y direction what the E field is and see, we're talking about how it's changing, of course, with time, but we can also talk about how much change it has over that tiny little distance x when it moves forward. And the same sort of thing, of course, we could then look at a little tiny bit of the change in flux, and of course we're not going to change the size of anything here. So in that case, we could also write this equation with a little bit of work as that same sort of length L, but in a different dimension. How much the magnetic field is moving along that same tiny little bit of change in the x direction, and then of course how much it changes with time. And again, notice I'm taking derivative of the B field only as a function of time. So all this is to do one particular thing. And of course, you see, I'm definitely not going through the details about how I get this. But the key point is that I can show that there is a relationship between how the electric field changes in space and how the B field changes with time. So, for example, that's basically to say that as we move forward, the electric field is going to change strength. So suppose that as we go forward, the electric field gets stronger. Well, in that case, then it's going to say, as we're moving forward, there's going to be then a change in time because we're moving at finite velocity. So move forward a little bit of distance, a little bit of time has gone forward. And so in that case, the B field has to have done the opposite, or needs to have, kind of reverse things as well because of that minus sign. So in a sense, then, it's that this side of the equation is also getting larger, but it's getting larger and more negative. So as the electric field gets larger moving forward, the B field is also getting larger as time is going on. And this according to just a bit of application of Faraday's law. Suppose now we did the same thing, but we used the Ampere-Maxwell law and try doing the same sorts of things there. Now, we're not going to actually have any charged particles, so there's no current that we use the letter I for, but there can be, again, talk of the changing electric flux, changing magnetic fields. So, if again we rewrite this aspect of the Ampere-Maxwell law in the same sort of way we did before, as somehow relating to the length that we have, some length in the, in this case, the z direction, and how the B field changes with distance x dx. And there should also be a minus sign from the derivation, but like I say, I'm not going into the details for why that is. Now, from the right side of the Ampere-Maxwell law, again, we're getting to ignore any currents because there's no charged particles here. But again, we can then look at the change in flux of the electric field as a function of time, and write that as similar to that we did before, dE dt. So from this work here, we can see that if we apply the Ampere-Maxwell law, and I'll write that out completely, without the, I'll include the current portion as well. So if we use this, so like I say, this will be 0 in this case, and so we would find then, from the same sort of work that we did in the previous part, that there is a relationship then between how the B field is changing in space and how the electric field is changing with time, and there being a few constants along the way. So let's use these two results of about changing B field in space, giving changing E field in time, etc. So from this I could ask the question, well, what if I decided to take another spatial derivative of the E field? So if I took this equation, I imagine doing dx to both sides, basically taking x derivative of both sides. I'd be taking the x derivative of the B field here, and I already have something that describes how that works and how it relates back to this. So if I were to then go through and do dE squared dx squared, that'd be equivalent of doing d dt dB dx. This is true from the first equation, and if we plug in for what we have here, then we're going to find that we get the following form. And of course, notice how the minus signs all disappear on us. So this now gives us a straightforward relationship then between how the electric field changes in x and how the electric field changes in time. And we can do the exact same thing for the B field. So you'll have to ask yourself, what sort of function could you possibly have that you could take two spatial derivatives and you get the same function back after doing two time derivatives and some constants out front? So again, think about what sorts of functions were there that you could take multiple derivatives of it and still have the same sort of function pop out. If we remember back to when we were doing waves, we found that the sorts of functions that did that well were the sine and cosine functions. Now, we, for the most part, when we first introduced that, had just a single variable thing. So we had, for example, the position of some mass on a spring going up and down, and so the function x was it was a function of time then. But here we need to have the E field as a function of both space and time. So we would find that this would actually work as if the E field were based on some sort of cosine function with both an x component and a time component to it. So in this case then, that if I just choose the right constants, and for the amplitude of this I'll just call it E max, for the amplitude of whatever this thing is. And so if I take two spatial derivatives, well then I have k squared popping out. If I take two time derivatives, I'll have omega popping out. And it should be such that then it could somehow relate to the other functions that we have popping out. Now, if we go ahead and do all the work, and I'm obviously skipping a lot of the work here, we're going to end up finding some interesting things. So back in this equation here, what this is going to equal to, you'll maybe notice this, like I said, this is ultimately allowing us to see that there's an equation form here, and what this constant ultimately is going to be related to is the velocity of the wave. Since this is ultimately, like I say, describing a wave, cosine function will fit this just fine. And so the speed of that wave is supposed to be defined as related to this term, so that if you have the velocity of whatever that is supposed to be 1 over v squared is equal to this constant. So this is a derivation from the general wave equation. So in that case, we might wonder, all right, so what should that velocity be? It's supposed to then be 1 over the square root of mu naught epsilon naught. And if you go ahead, plug in those constants and see what you get, you end up getting a number around 3 times 10 to the 8th meters per second. In other words, the speed of light. So from this work and realizing we have a wave equation and what terms are being described here, we've ultimately just derived that light is a wave with a certain speed. It has no charge from what we've seen here. We should also expect it to have no mass from other realizations, and that this wave equation can completely describe what's going on here for both the electric field and the magnetic field. So, what is light? From what we've just described now, we see that it is in fact an oscillating electromagnetic wave.